Number three, the improper integral from 1 to infinity, square root of 1 plus x over x cubed dx. Okay, so this is first of all improper because one of the limits is infinite. The one is okay. It'll still be proper. We're not going to be dividing by zero anyway. Okay, so if you follow along sequentially, in the first problem, I was talking about intuition to have. So let's think about it similarly for this problem. Again, as x keeps growing, our function square root of 1 plus x over x cubed will approach square root of x over x cubed. Oh, not approach, I should say, it'll start behaving like this because as x keeps getting bigger, who cares about the small plus 1? For example, if x is 10 billion, 10 billion plus 1, who cares about that small one, right? It's about 10 billion. Okay? So we can kind of simplify the square root of x over x cubed into 1 over x to the 2.5 power, 5 over 2 power. Okay? This integral, original guy, will likely converge since the integral from 1 to infinity dx over x to 2.5 converges, okay? So this is where the professor is not correct or is not precise enough. This might fly in his class, but I'm trying to cover all bases here. This might not fly in another professor's class, like your professor, if you're watching this and you're a student. This professor did not use the comparison test properly. So let me explain why. So it's good to have this intuition, but he's solely basing off of this intuition that because it'll behave like 1 over x to 2.5, and since we know that converges, then this guy will converge as well. And that's his solution. That's right there. He failed to see that our function is actually bigger than 1 over x to 2.5. Let's even graph it. So I have decimals open. Let me open it up right now. So this is the function that we want. Square root of 1 plus x over x cubed. Okay, now let me graph y equals 1 over x to 2.5 power, the one that the professor tried to compare to. You can see it's smaller. And even as we keep going, it's smaller than this curve over here, the one that we want. Okay, the comparison test doesn't work in this way that he's trying to do. Something smaller converges, but something bigger could possibly diverge. He didn't get the comparison test correct. So this might fly in his class and be okay in his class, but as I'm trying to say, if your instructor is or grader is very picky about comparison tests and comparing properly, you cannot say that something bigger, that something that converges, will converge as well. It's impossible. It's not always the case. It's not always impossible. It's not always the case because you're summing up more things, so it could possibly diverge. Okay, so in order to use the comparison test properly, we have to pick something bigger that converges as well. If something bigger converges, our thing that's smaller must also converge. This is the points that this Princeton professor missed and missed quite a few times in his solution manual to this problem set. Okay, so I'm trying to emphasize this point to use the comparison test properly because your grader or instructor might not mark your answer correct if you did what the Princeton professor tried to do. Okay, I would mark it wrong because I'm a picky grader. Okay, so we got to pick something that's bigger, as I was saying. So this will work. 1 over or square root of 1 plus x over x cubed is less than or equal to x over x cubed, which we can simplify to 1 over x. Okay, we can even double check since this on a test we would have to check by plugging in some values of x, but since we're not on a test right now, let's just double check graphically that this is true. Okay, so this is again the function that we want. So we're comparing with what? 1 over x squared, right? Look, 1 over x squared is bigger. Okay, we know that the integral from 2 to infinity 1 over x squared dx converges. Therefore, our original integral converges by comparison test as well. Or not quite, because our integral is from 1 to infinity. So we had to split up from 1 to 2 and 2 to infinity. So this one, we just proved by comparison that it converges. And this one's finite and proper, so it will converge for sure. So therefore, our original integral converges. Once again, to hopefully hit the point home, you cannot make this comparison. or this inequality is true, but you cannot make the comparison that since 1 over x to 2.5, this improper integral converges, then our original converges as well, because our function is actually bigger. We cannot say something bigger than something that converges will for sure converge. That doesn't even logically make sense. Hopefully that is clear by now, after I said it a few times, okay? Okay, so be careful is my point for these. You have to pick an appropriate function to use the comparison test properly. Hopefully this was helpful. I believe in the next problem, the professor made a very similar error, so please look up for that if you're interested and want to hammer this point home even more.